Hello, my name is Vitali, and I would like to present our tool for visualizing verification results. Software verification ensures that a program meets its formal specification. Static verification tools can prove correctness or report potential bugs. However, interpreting their results is often a manual, complex, and time-consuming task. Our tool addresses this challenge by presenting those results in a more accessible and human-readable way. This is the main page of the continuous verification interface. Here, all benchmark results are grouped by property. From this page, you can navigate to any benchmark to explore detailed verification results. This page provides a high-level summary of the verification of Linux kernel modules. It shows how many modules were proven safe, how many contain potential bugs, unsafe, and how many remain unknown. Now, let's take a closer look at the potential bugs. On the unsafes page, users can browse entries with detailed information about potential bugs. The list can be sorted or filtered, for example, to display all error traces related to a specific module. Let's look at an error trace found in a Linux kernel module during verification of clock API usage. In this case, we're checking that every call to disable the clock is properly preceded by a corresponding call to enable it. And here is the error trace itself. The interface is split into two panes, an error trace showing a step-by-step execution path from program entry point to the property violation, and the source code. To support manual analysis, our tool offers several key features. Firstly, critical operations that are most likely related to the bug are automatically highlighted. These so-called violation hints are taken either from the verifier itself or from the property. Secondly, the trace is displayed as a collapsible call tree. By default, only the branches containing violation hints are expanded, highlighting the most relevant parts of the trace. However, the users can manually expand any branch to explore additional details. Thirdly, each trace step links directly to its corresponding location in the source code, significantly speeding up the analysis process. Fourthly, low-level details, such as assumptions and declarations, are hidden by default to significantly reduce the size and complexity of the trace. Users can easily switch between the full and simplified views. In this particular trace, we see that after enabling this clock, the potential error path was not handled. We identified this error trace as a real bug and added a description. To do that, we simply marked the trace by filling in the relevant fields, so if it appears again in future runs, it will be automatically recognized. This particular issue was later reported and fixed in the mainline Linux kernel, as confirmed by the corresponding commit. Now let's open the results for the next Linux kernel version, where this issue has already been fixed. We switch to the list of safe results, which follows the same structure as the unsafe ones, and locate our module. Here we can inspect all extracted conditions from the correctness proof. To manually recheck the fix, we can filter the conditions by the same variable involved in the earlier bug. As shown here, the entire code path that previously led to the error is now fully covered, as well as the rest of the module. Returning to the main results page, we can review the unknown reports, most of them caused by timeouts, and inspect the corresponding verifier logs. We can also examine resource consumption. These quantile plots show CPU time and memory usage per module, helping to estimate the typical verification cost. Finally, the source code coverage view summarizes which parts of the verified subsystems were actually checked. The tool also supports regression verification, tracking how results evolve across software versions. When a user marks a trace, this information is stored and automatically applied in future versions. Here, for example, all unsafe results are already known. When many new error traces appear, for example, for memory safety, users can focus on new results first. By comparing benchmarks across versions, the interface automatically highlights new traces and proofs. In this case, there are only 7 new error traces out of roughly 1,000 total. You can learn more about our tool in the GitHub repository and explore the visualized results directly using the Docker image included in the artifact. Thank you.